In this video, we're going to have a look at the concept of period dilation of sine and cosine functions. Now, in the previous video, we had a look at how we could change the maximum and the minimum y values of a sine function, seen here, or we could have said or explained it as changing the range of a particular function like y equals sine t. In this video, we're going to have a look at how we can, guess you could say, compress and stretch out this particular function along the horizontal axis or the t-axis. So consider the function y equals sine t and the graph below. So in this graph, we've got on our vertical axis, this is y, and on our horizontal axis here, we've got t, and that's in the positive there and the positive there. And what we've got here is we've got a function, and say for the rotation, if this was mapped on a unit circle, if we rotate it around, we'd have a cycle or a period of 2 pi as such. Now the question at hand is, what if we want to fit two cycles of this pattern within 2 pi radians? Or what if we want to stretch it out such that we get half of this pattern within the 2 pi radians section here? And this is where the concept of period dilation comes in. So consider if I change this ever so slightly and I put in the value n in here, what we can actually do with this input here is change the rate at which this pattern here, so this pattern along here, change the rate in which it projects itself on the curve. Now consider going across to Desmos. What I've got here is I've got a graph, and the graph is of a sine function, and the one in red here, it is a sine function or its full domain, so all the real numbers. And over here I've got a graph in blue. Now I've just made a slight alteration and I've changed the horizontal axis such that it's now measured in radians. So going on, looking at this graph in blue here, notice that it's one full cycle, and the full cycle itself is what we'd expect. So it's got a period of 2 pi. Now, by introducing this n, so this value over here, by introducing the n into the equation here, what we can do is we've got a way of shrinking or compressing and stretching at the function. So notice when I increase the value of n, observe what's going to happen to the function itself. So by increasing it, we can actually fit more or repeats of the pattern within this part here. So over 2 pi radians, we can fit in 2 repetitions of the pattern. So that's increasing n. And by decreasing n, so decreasing it below 1, what we can do is we can stretch it out so we can get less than a full pattern or less than a full cycle within that 2 pi radians. So what this here is called period dilation. And we can define period dilation using the formula. So grabbing the contents in here, we can define the period of a function. We can say the period is equal to 2 pi over n. So n being the amount of patterns we want to fit into a horizontal change of 2 pi. So consider if I turn the period on now, so I'm going to get x equals 2 pi over n. So this purple line here is going to mark the period of this particular function here. So y equals a sine nt, where a is being set to 1. So if I increase the value of n, notice that a period, if I increase it by, let's say, we'll try and get it on 3 pi on 2. So if I increase it by 1.32, we get a period of 4.76 radians. And if I increase it by 2, notice the period of the function, the period of this function here, y equals a sine nt, it's going to increase, or decrease, sorry. The period itself will decrease to pi radians. If I increase it to 4, notice that we're going to get a period of pi on 2. So increasing the value of n is going to decrease the size of the period. And conversely, decreasing the value of n to below 1 is going to stretch out this function or this waveform, and we'll get a period of, zooming out, we'll get a period, so halving n, so n equals 0.5, we're going to get a period of 4 pi. Now if we decrease it ever so slightly again, so we'll go to 0.25, we're going to get a period of 8 pi. So notice one cycle of this waveform is going to occur, rather than occurring over 2 pi, it's going to occur over 8 pi. So this is what we call period dilation of the sine and the cosine function. Now if we want to get really fancy and we want to tie this into the concept that we were looking at just before, what we can do is we can do period dilation. So I'll speed up the period and we'll give it an n of, say, let's go 1.5. So that's a little bit different. And we can also add in the amplitude dilation. So changing the a, notice what happens. We can change not only the period of the function, so not only can we compress and stretch this function across the horizontal axis, but we can also do the same thing on the vertical axis at the same time. So let's hit play on n, hit play on a, and look at that funky behavior right there. Not too bad at all.